Hello, everybody. Welcome to our latest Hubble Hangout. My name is Tony Darnell. I am at the Space Telescope Science Institute, and it is that time of the month where...
Oh, great phrasing, Tony. I love it.
So it is time now for our monthly visit with Dr. Frank Summers, the outreach astronomer at the Space Telescope Science Institute, who keeps tabs on all of the really cool and interesting things going on with Hubble and shares them with us every. Welcome to our latest Hubble Hangout. I did it again. My name is Tony Darnell. I am at the Space Telescope Science Institute, and it is that time of the... I wish I had $1 for every time I've done this.
Okay. You're the expert here, Tony. So
okay, now I've got to figure out where it is. Gosh, darn it.
Your echo is coming out somewhere.
Oh, I did it again.
And you get to hear your mistake coming at you twice. So while Tony figures that out, I'll just say that it's always fun for me to be here, even if I am considered that time of the month for Tony. But what we like to do here at the Space Telescope is we really get a lot of fun out of taking the deepest discoveries from Hubble and explaining them in detail. Because for me as an astrophysicist, the really difficult thing is to have a wide breadth of all these various ideas and then be able to explain them to the public. I mean, because you're taking something that's at the cutting edge of science. What we do in our press releases, we're really at the edge of science, and we've got to provide all the context and all of the background information to bring it out to the public. And so this is what really, jazzes me about doing all of this stuff with Tony and with all the stuff we do in the Office of Public Outreach, is that understanding not just the discovery, but all the context and the background behind it. So, Tony, did I vamp enough to cover up?
You did great, thank you.
Thank
I found
you.
the tab that had the YouTube video in it and killed it. I have like 300 tabs up on my desktop right now, and every time I think I've get it, there's always one that gets through me. So, again, apologies for doing that yet again. But you know what? I don't think people would feel right if I didn't do that at least once during the Hangout. So
look, it's live, okay?
It's live, that's right. So anyway,
and it's free, so you're getting what you pay for.
That's That's right. So here we are. Another month has gone by. We have started, by the way, broadcasting the public lecture series that Frank hosts every month at the Institute. The first Tuesday of every month is now going on our YouTube channel. So we hope that you guys will tune in to watch that as well with us, because it's an easier way for you to interact. What we try to do is answer any questions and comments while it's going on. I'll monitor the Twitterverse and the comments on YouTube and try to respond to them while the lecture is going on. And Frank will do that to the extent that he can, but he's also got to run the show, so it's a little bit. He may or may not be able to respond to all comments. Okay, Frank. So what do we got? We got
Okay.
What's the latest and greatest with Hubble this month?
All right, so I know I did it live last week during the public lecture series, but I know a good amount of this audience probably hadn't seen it. But I want to go quickly through the news from the universe that I did last week, and then I want to go beyond what I did with the news from the universe and talk about a new section on Hubble site that I had a lot to do with, and I think is really, really cool. Okay?
Agreed. Okay, let's go.
So let me. I got to start my screen share. There we go. Starting my screen share, and I'll start the PowerPoint slides. Okay, so when I present this to the public lecture series, I call it News from the Universe, and this is the stuff. This is the stories I chose for May 2014. So my first story I called 5 Golden Rings. For those of you who know the Christmas song, well, it doesn't have anything to do with the Christmas song. So what we're talking about is looking at and discovering new information in old data. Now, I bring up this image. This is from the Keck telescope, not from the Hubble. This is of the star HR 8799. Well, actually, it's of everything but the star HR 8799, because
so is that like a star from the 60s or something? It looks like,
yes.
A tie-dye star. What's up with those colors?
This star went psychedelic on us. No, all that psychedelic glop in the middle is the residue after subtracting out the light of the star. right? If you're trying to look for things around a star, you've got this honking bright star that you've got to be able to subtract out. So the folks at the Keck Observatory subtracted out the light of the star, and that psychedelic residue in the middle is the result of that subtraction. So you got the star mostly subtracted out, but the red dots around it are 3 planets
The
that
one
were
that's in
discovered.
July?
Yeah, the ones that, well, the red dots, and then there are the pluses to show where the planets were observed in July 2004,
Oh,
and
okay.
the dots show where they were in 2008.
Got it.
Okay, and showing that they're moving around this star, right? And so this was one of the first discoveries of actually observing planets around another star. And this was actually done with the Keck telescope from the ground in the infrared. Now, we here at Hubble didn't do this. This was again from Keck. But what we did with Hubble is we came back a couple years later, and we looked not at a new image of HR 8799, but we looked at an old image that was in the Hubble database. All right, the Hubble archive has got lots of cool data in it, and so people went back to it, and you see on the left the incredible brightness of the star HR 8799 as it was observed in the Hubble database, the Hubble archive. Well, subtracting...
So you can see a bunch of, so what you're looking at is a bunch of diffraction spikes from the telescope, and then there's the saturation in the center. That's the star, right?
Right, exactly. And the thing about Hubble is that over the years we've learned the characteristics of Hubble incredibly carefully. And one of the most important characteristics is called the point spread function. So here's some cool stuff that I can give you that I can't do to the normal public audience. And so the point spread function takes, I mean, stars are points of light. And it's a very faint point of light. It appears as a circular dot. And as it gets brighter and brighter, it becomes bigger and bigger dot. And then it starts to develop these diffraction spikes and all of this stuff around it. And so with Hubble, we've gotten very good at characterizing how that point spread function grows and what is the shape of the light that is put onto the detector. Using that information, we can very, very carefully subtract out the point spread function due to the Hubble detector, pull out that star, and in the right-hand image, you again see 3 dots of light. And those are the planets, yes.
Oh, okay, those are the planets, yeah.
Right. Those are the same planets that Keck had discovered a few years earlier. But the important point was this image was taken, I think it was 8 years before the Keck discovery. So it adds to the baseline of this discovery of the planet. So we have more points in the orbit for these planets around its parent star. And that's really important. I mean, when we discovered Uranus, the first thing people did was go back into old data to see if you could, determine its orbit more accurately by having a longer baseline of the data. Well, we're doing the exact same thing here with extrasolar planets.
So now we know what to look for. We know there's planets there. They just went back and looked at what previous observations of the Hubble and got this information out.
Okay, so this is an old story. I may have talked about this before, but the point is that we've got this really good way of subtracting out the light of stars, and we wanted to do it not just for planets, but we also wanted to do it for dust disks around stars. So these are 2 dust disks, one on the left, AU microscopy, one on the right, HD 107146, and you can see also the size of Neptune's orbit for scale. Again, in each of these images, the light of the star has been blocked out. In this particular characteristic, not subtracted out later on, but blocked by a spot of light on the a dark spot on the detector called a coronagraph. So
they block the light out.
Yeah. So they block the light of the star in the detector. They have actually a place on the detector window where there is a dark spot, and they can place that dark spot over the star to block out the light of the star and try and see the material around it. Now these, of course, are our 2 best examples, the one on the left being an edge-on disk. These are flat as a pancake, and they're disks of material spinning around the stars. The one on the left being edge-on, the one on the right being face-on. And of course, as press release images, they are really gorgeous and beautiful and everything, but most of our observations of disks aren't quite so good. Some of them are like we see in this next image here, HD 181327, and On the left, if we were trying to take out the star to try and see the disk, okay, this again is the PSF removal, point spread function removal. The normal one that we had been using would show you that there is a ring of material around this star, but there would be a lot of bleed of the star into that ring, and you wouldn't be able to measure the characteristics of that ring very carefully. Well, the new method they've come up with, they call it KLIP. I don't know what that stands for, but it's the new method of point spread function removal, removes the star more carefully and more completely, giving us the much clearer view of that ring on the right in the right-hand picture.
I mean, you can still see it with the standard PSF removal, but you get a much better one with this new technique, it looks like.
Right, and you're really getting rid of the star only, so that the measurements of, say, the thickness and the density and how much material is in that ring, which is really important for understanding, what stage the planet formation is in this system. Because I guess
does that mean those little bright spots in the center there? Those are actually real then?
Nah, I wouldn't trust the stuff inside the ring.
Oh, okay, all right.
Again, you're getting really in close to the star there.
Yeah.
But
okay.
You can see how the bleed around the ring, both interior to the ring and external to the ring, is greatly reduced. All those radial striations, the lines heading out in radial directions, are greatly reduced by this new PSF removal technique.
Okay.
And that
now,
helps.
all telescopes do this, folks. I mean, it doesn't matter how perfect your telescope is. The PSF is this thing that smears it out. You could have a perfect point source of light, and all optical systems are going to smear it out a little bit. And the manner in which it smears that out is you can model that and measure it and model it, and that is what he's talking about. It is called the point spread function, and you can remove that effect. So if you had a point of light that got smeared out into a circle, little bit, and then you knew the point spread function, you could remove that point spread function to get your point back. So that's what's going on here.
Right.
But my question, Frank, is how are they able, do you know, to determine which light belongs to the star and what doesn't? I mean, how do you figure that out?
Okay, well, you're going to calibrate your point spread function by looking at a star. I mean, stars are perfect points of light.
Right.
I mean, the stars are so small compared to their distance away that they are a point of light. And what you're going to want to do is find a uncrowded field where you're observing just a star and not a star that has any, and you want, an older star that wouldn't have a disk or such around it. All right? You want to be able to get your, with each detector, you want to be able to get a set of calibration images of various stars that are uncrowded fields, so you can get a clean view of the point spread function. And then you can, by getting a whole suite of these and measuring them, you can get you can do an average of those various calibration images to get a pattern that develops through the point spread function.
Yeah, I can see how that helps you identify the star, but not the flux or the pixel values of that star. So how do you know when to stop removing?
Well, then that's the art part of it. Okay. If you've got if the point spread function changes with the brightness of the star, right?
Yeah.
So in doing this PSF removal, you're going to have the spectral type of the star as a variable. You're going to have the magnitude of the star, the apparent magnitude of the star, the brightness of the star as another variable. So you're going to do a sort of a least squares fitting with the different variables that you have that make up your PSF, and say where in if I change these variables, does the fit get better or worse? And then you find the one that gives you the least amount of error.
Okay, that makes sense, sure. So, and I guess that's another reason why you don't want to totally trust that area where you remove the point spread function, because you don't know how good you did totally.
Look, when I was doing my PhD thesis 20 years ago, the PSF removal you see on the left here would have been fantastic. I mean, it would have been better than you could ever hope for at that point. So we're getting better all the time.
Sure. No, this is amazing. This is really smart stuff.
So let me give you a couple more examples. So what we announced last month was looking at some disks around it in archival data. So again, we're going into images that Hubble's already taken, not partly to study disks, but it's already in the archive. And so here on the left you have HD 141943, which is a mostly edge-on disk. We've got the artist depiction below to sort of guide your eyes to seeing that disk. And on the right, a somewhat face-on disk, 191089, and here are the results using this new PSF subtraction. These aren't the only two. These are the ones that we illustrated with artist depictions. On the next one, the final image of this story, we have, of course, the 5 golden rings of the title. We have 5 really good detailed images of rings that arise from this PSF subtraction that we could not have gotten otherwise. And you can see they're still pretty ratty. But without this PSF subtraction, certainly the ones on the right would be very hard to tell that there was a disk there at all. Cool?
Yeah, I'm with you. This is nice. This is really great.
You usually jump in with some sort of comment as I.
Well, that's because I'm cutting and pasting some things in the comments.
Okay, well, this is the problem when I have my screen share on and I can't actually see the.
Yeah. So I'm just adding some comments here so I can make sure I get them all. That's all. Yeah.
Okay. Cool.
I'm with you.
All right, let's go on to the second story. Second story I called a tail spin breakup. All right, and that again is a play on words, as I like to do. But let's go back to last year, 2013, and this has got to be one of my favorite images of Comet ISON. All right, this is from Damien Peach. I believe he's a British astrophotographer. Absolutely fantastic images of Comet ISON last year. Huge kudos to him because he did some fantastic shots. This is one of the coolest ones. This is from November 15th as ISON was heading into its perihelion. And we all remember what happened, or really what didn't happen during its perihelion passage. This is the image from SOHO, time-lapse image from SOHO, where Comet ISON comes in, swings past the sun, and it breaks up on its way out. So we have seen comets break up, Comet ISON being the spectacular breakup that occurred last November as it passes the sun. But we've also seen comets break up not when they're passing right by the sun. Comet Schwarzmann-Wachmann 3, one of my favorite comets to say, just because its name is so cool. This is the breakup captured by Hubble of Schwarzmann-Wachmann 3, or we'll just call it SW3. And
Wachmann.
Yes, keep saying that 3 times fast, right?
Wachmann.
So we've got April 18th on the left, April 19th in the center, and April 20th on the right. This was back in 2006, and you can see all the pieces that broke off of that comet were flying off. Matter of fact, this wasn't the whole comet. This was just fragment B, and I believe there were 10 or 12 of these fragments. This was just the fragment B out of I think it went up to J or K or something like that. So we have seen comets break up elsewhere. Now, this is sort of expected because comets are these snowballs. And snowballs, you bring the snowball past the sun, it's going to melt, and its structure can become brittle, and it can break apart. What we didn't expect to see is something that I'll show you on the very next image. And this is the breakup of an object that's not a comet. It's an asteroid. This is asteroid P2013R3, and you'll notice that 2013 is in its name. It was discovered just last year, in September of last year, and it was seen to have some interesting structure that they believe they saw 3 spots. That it was a couple fuzzy spots. And here's what it looked like on October. So they got Hubble time to observe it based upon its unique characteristics. And this is the image on October 29th. And here is the image on November 15th. And here is the image on December 13th. And then again on January 14th. So here's a composite of all 4 of those images. And so over last fall and into the winter, we watched the breakup of an asteroid, not a comet. How cool is that?
Yeah, that is not.
Now, we don't expect asteroids to break up because we think of them as rocks, right? And that, you would, even if it's a rock is hurtling through space, and you could heat up a rock, and it's not volatile with the ices of a comet, so we wouldn't expect it to break up. But there have been a couple, two major models of what the internal structure of an asteroid is. Now, for the larger asteroids like Ceres and Vesta, we believe that they are these differentiated, very large objects, like planets or mini planets or moons, etc. But the smaller asteroids, well, they could be single objects that are, have chemical bonds holding them together, or they could be what astronomers call rubble piles. As in agglomerations of individual rocks that sort of are held together by their mutual gravity, and that they don't have the chemical, they aren't a single object altogether, but they're multiple objects together, or they're loosely held together, or the structure is not in some way fully coherent, right?
Mm-hmm.
So this is the question for this. If this was what we call the rubble pile model applied here, how would you then get it to break up? And the best guess for this, and I'm going to say this is a hypothesis, it's not proven yet, is that if you have the rubble pile, all right, and it has this incoherent structure, and you start it spinning, and you can use the torque. There's a very small torque due to light that you can get on this. You can get this asteroid spinning and spinning faster and faster. Then it could get to what we call the breakup velocity, where the centripetal force pulls it apart, can break it apart, and pull apart this rubble pile. And so the Dave Jewett from Hawaii is the gentleman who's doing these observations, and that is his best guess as to why we're seeing an asteroid for the first time falling apart. That if it got spun up to breakup velocity, and the pieces started coming apart. Now, we don't know that is true yet. We will continue to follow it, and we'll continue to model it to see if the torques really can produce something to get it up to break up velocity. I, as an astronomer, think about it and go, wow, it's got to tap. You've got to have that very, very, very small torque over a really, really, really long time in order to spin it up that fast. But then I always recognize that, well, this asteroid's probably been floating around the solar system for a few billion years. So even a tiny...
Did you already say what kind of orbit it had? I might have missed that part.
I did not say what type of orbit it had. I do know that it is not in the main asteroid belt, but it is not a sun grazer type thing where it goes in close to the sun.
Okay, that was, I guess, that's where I was heading with that. I wasn't sure if the sun might have been involved in some way producing that torque or not.
Well,
but
the sun would be involved in terms of the light pressure.
So the solar wind would do something. It's just...
It's more this radiation and
radiation pressure,
radiation torque on it, especially if it's got different absorption because of different surface elements. So
sure.
it absorbs.
Yeah. So you have highly reflective and some dark spots. That's gonna put some weird forces on the surface. Is this the same kind of torque that JWST's got to correct for with its momentum flap, or is that something else?
I don't know enough about JWST's momentum flap but it might be.
Okay, I wasn't sure if it was the same sort of force or not.
Well,
but
in as much as the solar shield is going to be absorbing radiation, and if it absorbs more radiation on one side than on the other side, then that could definitely throw a torque onto the whole spacecraft.
Okay, so it may not necessarily be related. It just came to my mind when you were talking about this, and so I
these are the cool things that we get to talk about.
So how bright was this thing? Do you have any idea? What was it? Something you needed a pretty big telescope to check this out, or?
Do you have
any idea?
I don't have a good idea, but it was not particularly bright. I mean, no asteroid is very bright, right?
Right.
So we're getting down toward 20th. We're getting down 15th to 20th magnitude
Okay,
here,
so this is
probably.
pretty much outside of most amateur scopes.
That would be my guess on this. I don't have the printout of the press release in front of me.
Yeah, yeah. No, I'm sorry. I just was curious. It was
Hey,
something that people might have been able to check out themselves.
I love it when you ask questions that I don't know the answer to.
That's my job.
All right. All right, let's go to the third story here.
Okay.
And I call this a Hubble Anniversary Present Part 2. Last month I talked about the Hubble Anniversary Present Part 1. And just to remind you, we talked about April 24th, 1990, one of my favorite shots of the space shuttle blasting off.
Special day.
A very special day. It's got the Hubble Space Telescope inside the payload bay. And then an amazing shot from the very next day, taken by the IMAX camera in the payload bay for the deployment of
One of the
the
few
Hubble
times
Space
you'll
Telescope.
see that front cover closed too.
Yeah. I know very few other times. I mean, except for when it's being serviced, that is almost never closed.
Yep. Yep.
But this was a fantastic shot. I love how they arranged to have the sun in the background for this shot.
Oh, I know. It's good. And you got the reflection of the Earth in the front cover there. It's really neat. It's really
right. The cinematographer just nailed that one. I think the only thing harder to do. I remember on the movie. Do you remember the movie Top Gun? Right.
Oh yeah, yeah.
And Tony Scott directed that film, and they were doing a shot on the flight deck where the aircraft were landing, and suddenly the boat starts to turn. I mean, this is a real Navy aircraft carrier, and it starts to turn to head towards wherever it's going to. And the director calls up to the bridge saying, no, you can't turn. I need the sun where it needs to be here for this shot. You got to give me half an hour more on this course.
Oh, so who's in charge, I guess, right?
And so the bridge called back down and said, well, that'll cost you. And he said, I don't care. I need it. So they actually turned the ship back to its course so they could have the sun where they needed it to finish filming that sequence. And I can imagine the only thing harder than turning an aircraft carrier just to get a shot would be to reposition the space shuttle just to get the shot like this.
Yeah, really. Oh,
I can't imagine IMAX calling down to Houston. No. We got to wait. Not for the. You can't release just yet. We have to wait till the sun is in the right spot.
we have a problem. So that blue thing there is probably that's either a lens flare or a
the blue alien dot with the red circle around it. Either that or it's one of Hubble's images of planetary nebulae. No, that's definitely a lens artifact.
Yeah.
Things. Okay, so back to Hubble instead of other movies. So that was 24 years ago, and last month in Rome they had the scientific meeting called Science with the Hubble Space Telescope 4. This is obviously a series of meetings about the Hubble Space Telescope. So to celebrate that meeting and celebrate our 24th anniversary, we actually released the Hubble 24th anniversary image a month early. We released it during this meeting so it could be unveiled at this meeting to the scientists at this meeting. But what I showed you that image last month, but what I didn't show you was the overview image. So this is a visible light image of NGC 2174, also known as the Monkey Head Nebula. And as noted here, it is not from Hubble, of course. This is from an astrophotographer named Richard Crisp. Always want to credit our sources here. And that square box up there is where Hubble took the 24th anniversary image. Now, this is a visible light image, but Hubble took the 24th anniversary image in infrared. Hubble, covers visible light, a little bit of the ultraviolet, and a little bit of the infrared. And here was that really cool Hubble image of that these pillars in the Monkey Head Nebula in infrared. And to me, it reminds me a lot of the Horsehead Nebula image released for the Hubble's 23rd anniversary, in that you're getting this dark gas, the stuff that's absolutely opaque in visible light, and being able to see a beautiful glowing gaseous landscape by looking in the infrared. The infrared has longer wavelengths, so it penetrates deeper into the gas. And also, this gas is cool. It's not hot enough to shine using invisible light, but it is warm gas that's hot enough to shine in infrared light, so we can actually observe more of the gas with the infrared for those two reasons.
Wow, that's amazing. So this was the small subregion in that larger picture you showed before.
Right.
But this isn't all, is it?
This is not all, because another thing I didn't tell you last month was that Hubble had observed this very pillar previously. This subsection here was released 5 or 6 years ago as a visible light shot. So here is that cropping to that. On the left, we have the Wide Field Planetary Camera 2 image using visible light of these pillars in the monkey head, and on the right we have the infrared version of it. So that's kind of cool. We've got this visible, and you can see the darkness that you see visible, and the what you see more, the way you look through it. One of the cool things to look for is just above the pillars on the right-hand side. I don't know if my mouse shows up on this, but there's a galaxy sitting right here next to one of those sort of bullet trails, right? Yeah. Next to that top bullet trail, just to the right, there's a galaxy, and actually 2 or 3 galaxies that you can see through the nebula. And you can't see that at all using visible light. That just shows you how much the infrared light penetrates through, completely through the nebula here.
I know, and to see what Frank's talking about in more detail, anything that's black on the left side image or very dark the light is being completely blocked. But here, if you go to the right side, you can see those regions are not dark any longer, and that's what he's talking about. The longer wavelengths are able to pass through some of that material. And those, what did you call them? That thing, the
I called it a bullet trail type thing.
Bullet trail. So the bullet trails are really stark. Those are really stark in visible light. And they're a little less so here in the infrared, but they're kind of glowing a little bit in the infrared too, so that's kind of neat.
Yeah, I'm just called them sort of like the bullet trail simply because remember the movie Matrix? Let's go back to old movies again, and the bullet trails in the scenes of the bullets flying through the air. That's what it sort of looks like here, but these are actually the wind blowing past these dense knots of gas.
Yeah, that's true. Yeah, that does look like that. I would have called them tadpoles, but I'm not as imaginative as you are.
We can do tadpoles too, but we have another name. We have another thing that we call tadpoles. Those are in the Orion Nebula.
Oh, that's right.
The Prophets in Orion, right?
Yep.
Okay, so here's we're finished with the setup here. Now the set is that we've got this visible light image, and we've got this infrared image, and we've got the contextual image that I showed you. So what we really want to do is take you on a full exploration of it. So I'm going to show you a movie, and again, this being a Hubble Hangout, it doesn't always show well. So I'm actually going to, let me just give you the URL first. Okay, so here is the URL, hubblesite.org/newscenter/archives/releases/2014/18/video/B.
Yeah, I put that, by the way, it's in the event description, so you can just click on it.
Right, so I talked it through, making sure you had time to drop it in there.
Well, I did before we started, but yeah, it's in there now. It's in the Hangout description, or the event description.
All right, and then this other URL, hubblesite.org/videos, we'll talk about in just a second. But I'm going to escape out of PowerPoint because PowerPoint often has problems playing videos. And I'm going to change my screen share. There we go. Get rid of the screen share, and I'm going to screen share with you this. Right, just the movie. I'm going to play it in QuickTime instead. All right, we up in the movie?
Yep, I can see it.
Okay, great. So, actually, I need to rewind it. I've shown you the end. Here we go, from the beginning. Now I'm playing it. So you can see the Orion constellation and the Gemini constellation here. And we're going to zoom into into the Monkey Head Nebula, which is located between Orion and Gemini. And I think it's technically in the constellation of Orion. So there's the whole view of the Monkey Head Nebula. Then we're going to move into this very small pillar section here, and we're going to show you Hubble's visible light image. Now we're going to go from 2D image to 3D model in the infrared. And we're going to slowly pull back. This is a 3D model that our team here of visualizers put together by taking apart the image and then putting it back together in a three-dimensional computer model and give you a three-dimensional feel for the structure.
You've talked about this technique before in another talk that you had given too. Remember the visualization talk? So that's on our YouTube channel as well, on how you model some of these things.
Right. I think that was the Truth and Beauty talk I gave in Texas.
Yep.
I also gave that as a public lecture series,
yes.
although we didn't hangout cast that one on YouTube.
No, but the one in Austin is. So.
Right. So what we did, and you can you can go to the link that Tony posted and see that. But what I really wanted to show you is if I go to my screen share again and share my web browser. There's my web browser. All right, that we have a new section on Hubble's site for sharing these videos. All right, and so is my web browser up? No, it's not up. Tony's looking at me funny. Go to my screen share. Choose desktop 2, or no, there we go. And start screen share. That better? Yeah, that's better. Now I look. Okay, so this is our Hubble site webpage, hubblesite.org. And you can see that up in the advertising box up here, it says Astronomy Videos. Go to the page. You can click that, go to the page, and get there. If you go down to the middle of the page, you can see a link to videos. Astronomy features and visualizations bring space science to life. We got it there, but we also have at the very top of the page, along our menu bar, we have that thing, videos, 3 ways to get to it from the home page. We're pushing it this month, aren't we?
Yeah.
If I go to that page, you can see that we have a collection of videos. Right now we are featuring this movie, which I called Evaporating Peaks, Pillars in the Monkey Head Nebula. And if I scroll down, you can see we have that Horsehead video from last year. We have some star clusters. We have some JWST. Actually, along the left-hand side here, we've got categories. So we've got videos about planets, some Jupiter and Saturn videos. We have some stars, star clusters, and the constellation of Orion. We have the nebulae, which I gotta say are our bread and butter because the nebulae are really, really cool. We have amazing shots of nebulae. We have some galaxies stuff.
That's actually my favorite. You could talk about that one, that the galaxy collisions, the simulations versus observations.
Okay,
that one's amazing. That's one of my favorite ones.
I will go into that and I will bring it up. All right, and you can see that on if you go to each page, we have the YouTube link to it, so you can watch the visualization from YouTube. All right, and you could make it full screen or anything. I'll just let it play in the background while I talk here. But you also can see that we've got lots of information about this. Now, this was one where we have a bunch of colliding galaxies. We had 59 galaxy images for this press release of galaxies that were colliding. And so I took a computer simulation of 2 galaxies colliding, and I matched it to 5 different stages in the on the galaxy collision. So there are 5 different images from this set of 59 that I could match to one computer simulation and show you how that each image from Hubble is just one snapshot in a really long process. And really long, I mean 1.5 billion years.
Yeah, that just blows me away, because you think about what Hubble is showing us when we see galaxy collisions, and then you run it with, you put it in the context of that simulation you have, this model that you're running, really is a great way to see that every single one of those 59 images are at some point a point in time of a much longer drama of these galaxies interacting. And so that's my favorite thing. That's one of my favorite ones you've ever made. Now, this is a big effort you're going through. You're going through, so people need to check back a lot on this website, because Frank is adding to this all the time, right? I mean, you're going back and putting visualizations up that you've had sitting around on your computer for a while, right?
Right. What we're doing is we're going back through all of the videos that we've produced in the past 10 or 15 years, and we're taking them and we're where we can, we're re-rendering them at full HD, 1920 by 1080. You'll notice on News Center and in Hubble site that we generally release things only at 1280 by 720 at maximum resolution.
Yeah.
I've worked in IMAX films. Okay, that's not good enough for me. I want the full HD, right? And so we're making available. And if you look on my the web page here, I'm going to just highlight the right-hand side are these download options, right? Oops, there we go. On the right-hand side, you've got these download options, QuickTime, WebM, and Windows Media. You can get them at full HD resolution to download and play on your computer. Astronomers also appreciate this because they download these and use them in their talks or in their classes. When you say that you love this one, I have to say that my colleagues loved it because it is used in so many Astronomy 101 classrooms where they can show off what's happening and relate the simulation to the visuals, to the observations.
Yeah, I'm glad you said that because I was going to say this is a great resource for educators too, of all ages, all grades and stuff. They can use these in their classes. So yeah,
Okay.
go to the site, guys. Download this stuff. It's all free. You can use it however you want. And
let me highlight one more thing.
Okay.
Because the other thing that we've got on here are stereo 3D versions of these, right? Because we have been, since we did the IMAX film Hubble 3D back in 2010, we have been experimenting with stereo 3D. So as you can see, we've got, 6 different visualizations right now on the website that have stereo 3D versions. So if you own an HD TV with stereo 3D capabilities, you can download these movies. Generally, you play them through the media player of the television. You put your TV into 3D mode. These are side-by-side versions. So you put your TV into the 3D side-by-side mode, put on your glasses, and then you'll see the Hubble images pull out into 3D. It's not just seeing a 2D version of our 3D models. You're actually seeing them extend out both in front of the television set and behind the television set.
Yeah, they're really beautiful. So what software do you, I mean, I get a lot of questions sometime about this. What software do you primarily use to put these together with?
Well, when we're doing the stereo 3D ones, most of the ones here use a software that's called, from Autodesk, called Maya. It's the same software that Hollywood uses for most every blockbuster movie that you see that uses 3D visualization probably uses Maya. There's others, Lightwave and Houdini and a few other things, and there's even the open source Blender 3D modeling software that's available. But we happen to be using Maya. Then, of course, we use all sorts of things to prepare the images, whether it's GIMP or Photoshop or other things. And since it's scientific data, there's oftentimes that I will need to use my own software or some scientific software, write code that transforms the science data into a suitable format for using in the visualization. If I've got 10,000 galaxies in a visualization, I'm not going to go by hand and place 10,000 galaxies at 10,000 different 3D positions in space. Instead, I'm going to write code that will write out a script that will then do those 10,000 positionings for me. So it's a good combination of scientific software, custom software, off-the-shelf commercial software that we use in our productions.
So how did you get into this, Frank? How did you get into the visualization part of it? You started out as an astronomer doing research, and you also, but now you're huge in making these these visualizations. How did you get into it?
Well, it was actually kind of funny because it started when I was doing a postdoc at Princeton. After I did my PhD at Berkeley, I came to Princeton to work with Jerry Ostreicher and David Spergel. And we were part of something what we called the Grand Challenge Cosmology Consortium, doing computer simulations of how galaxies form in the universe. And we were approached by some folks who were making an IMAX film, the IMAX film Cosmic Voyage. And they wanted to do an evolution of the universe from the Big Bang to the formation of Earth. And so they came to us as the Cosmology Consortium saying, all right, well, how do we draw the early stages of the universe? Tell our artists what to draw to show the formation of galaxies. And then we sort of showed them our computer simulations and all the complexity and all the detail that we had in these computer simulations. And they said, wow, that's kind of cool. Maybe we could use your simulations instead of asking artists to draw it. So my PhD thesis, I scaled the simulation up by a factor of 10, ran it on the largest supercomputer of the time out at the National Center for Supercomputing Applications, and my data appears in the IMAX film Cosmic Voyage.
You were hooked from that point on.
Well, during that process, I served as not just a data provider, but also I became the main liaison between the astronomers and the visualizers out at NCSA. And I found that I had...
National Center for Supercomputing Applications.
Exactly. They had a great, wonderful
Champaign,
visualization
Illinois.
group. Yep.
Yeah.
Wonderful visualization group out there run by Donna Cox. And Donna and I found that we could... She's an artist, I'm a scientist, but we could meet in the middle and we could chat very well. And I found I was a really good translator of the science to the art side. And that, understanding one and being able to explain it to the other and vice versa was a really good role for me. So that got me hired at the Hayden Planetarium to work on the exhibits for the Rose Center for the Earth and Space that opened in 2000, and I've been doing lots of visualization ever since then. And so my job has moved out of doing scientific research, slowly moved over the years from 1994 on. My job slowly moved from doing scientific research in cosmology and how galaxies formed to doing the public outreach and doing the visualizations that I love to do so much now.
And how important do you think the scientific background is for doing this kind of thing? I mean, I'm trying to imagine somebody who's very interested in doing these visualizations, but maybe isn't a scientist. How would you weigh that ability to be able to do, like you said with Donna Cox, where to translate the science into a more artistic thing? Do you think that's a very big part of what you do, and would you recommend that anybody else wanting to get into that have a pretty heavy science background?
Well, if you want to do it right, I think you have to not have a science background, but be willing to collaborate with someone who does. This is what makes Donna
understand whatever it is he says.
This is what stood Donna apart from the beginning, and what we strive for here at Space Telescope is that we want to achieve a verisimilitude of science, right? We can't get it exact. We're not going to be perfectly scientifically exact. This is a movie. This is, you want it to be entertaining, but we don't want to misteach. We don't want to put in misconceptions. Can I rag on Cosmos, Tony? Do you?
Sure.
Okay, I mean, Neil Tyson hired me at AMNH. He's a great friend of mine and everything. I'm not trying to rag on Neil, but I'm going to rag on their computer graphics folks, okay?
All right.
Because their very first episode of Cosmos had 3 howling errors of computer graphics in the first, 15 minutes. And it really bothered me, because this is what I do for a living, okay? This is what I really care about. And let me just give you one...
They took the artistic license a little too far, then.
I'm saying they had Hollywood computer graphics guys doing it, and they didn't have a scientist doing the oversight, okay?
Wow.
So, for example, their Spaceship of the Mind, right, that little silver flying wing, was flying through the asteroid belt, right? And it was dodging asteroids, as if the asteroid belt were this, densely packed with asteroids.
Like in the Star Wars film, right?
Exactly. These are guys who grew up, they saw Empire Strikes Back. They know that, if you go into an asteroid belt, it'll be dangerous, and you have to swerve the ship back and forth through it. That's total BS. The asteroid belt is totally empty, right? You could fly through the asteroid belt and never, ever see a single asteroid. And that really bothers me.
Would you go so far as to say they were misteaching then?
Yeah, that is misteaching. That is reinforcing a misconception that has been around, certainly since a lot of sci-fi movies have adopted the idea that, the asteroid belt is dense, it would be dangerous, you don't want to fly into an asteroid belt. And that's just wrong. At least in our solar system, the asteroid belt is really, really sparse. And you have to work really, really hard to get anywhere near an asteroid. You think of our missions, to the Dawn mission that's going to approach Ceres next year, right? We're working pretty damn hard to get it anywhere near Ceres, right? That's a complex trajectory just to get there. So, you know, you don't accidentally come upon an asteroid very often, right?
Yeah, that's true. And we've sent many probes out into the outer atmosphere. Well, not many, but we have sent some out into the outer solar system, and there's been nothing really to worry about. We just send them straight out there, and they.
Right. Actually, I mean, the one place we did have to worry was the rings of Saturn. Sorry, the ring plane crossing of Saturn for Voyager. We worried an awful lot about that. Turned out to be just fine, but that was one place where we know there are literally millions to billions of particles in those rings, and that's someplace that you do have to worry about it, but not the asteroid belt. Anyway, that's just one example of the carefulness that you want to take with computer graphics. That I want to make sure that the science is presented accurately, it doesn't misteach, but it doesn't have to be perfectly accurate. Right? I mean, your cameras are always flying faster than the speed of light. You have to speed up and slow down time. You have to show some things that are invisible to the human eye. Yeah, there's artistic license you can allow, but you want the main messages to be strong. And I really, you know, when professors say, "Hey, I use your visualization in my classroom," that's one of the greatest compliments they can ever give me, because it shows me I've got the basics down and that it's worthy of using as a teaching device, not just for entertainment.
Exactly. So I would encourage anybody who's interested in this to take a look at these visualizations that Frank's created, and he also works with others at the Institute to make these, and he has a great team of people, and they are astonishingly beautiful. I just no, these are like, I mean, my first video I made in 2006 was on the Hubble Deep Field, and there was this, you know, Frank had done a visualization where we kind of flew through the ultra deep field, and you know that was just one example of the kind of stuff that he did. And even then he was careful to say, you know, I had to squish and scale those galaxies. You know, those galaxies aren't really that close together. So anyway, they're amazing stuff. They're the source of a lot of good material for videos that I make as well, and I just think everybody should check them out, and let us know what you think. I mean, you know, give us some feedback. Let Frank know, let me know, and keep checking back, because he's adding more all the time, right?
Right.
Do you have a schedule, or is it just whenever you feel like it?
I would like to be on a schedule of every 2 weeks. Okay, to be honest with you, I'm trying to get a new one out every 2 weeks. Matter of fact, this week we've got the stereo 3D version of the Monkey Head Nebula coming out. Okay.
Okay.
So the evaporating peaks in 3D. We finished rendering it. There was one problem in the compositing stage that we have to fix, but that should be out hopefully Friday. Although I am going away tomorrow. I'll try and get it out Friday, if not very early next week.
Okay. Well, like I said, I just want to know if there was a schedule, but people should periodically come back on order every 2 weeks, maybe 3 weeks or something.
And then, of course, the other thing they can do is they can follow us on YouTube, right?
That's true. They get everything gets posted on our YouTube channel. That's youtube.com/Hubble Site Channel.
Right.
And it'll take you right there.
I pulled up the page. Let me screen share this. All right, there we go. So there is, I gotta kill my bookmarks. Don't need to share my bookmarks across the thing. All right, so there is our Hubble Site channel on YouTube, and you can see that if I scroll down, we have a whole suite of astronomy visualizations. This is the playlist that the new visualizations get added to, as well as lots of other cool things that we post. So,
right, so if you want to know more about just which new visualizations have been added, you want to subscribe to that playlist. You can subscribe to playlists and get notified when a new video comes up. So I highly recommend you doing that. And also, while you're at it, do the Hubble Hangouts playlist as well, so you can get notified when we have a new Hangout posted as well. So,
all right.
Okay, well, thank you, Frank. I guess we'll be back next month for more news from you on Hubble and across the universe. I want to remind everybody that our next Hangout is a week from tomorrow. I was hoping to get it done tomorrow, but Dr. Amy Simon couldn't make it. I can't really talk much about what it is because the press release hasn't come out yet.
Let me just tell you, it's really cool, okay? You're going to want to see this one.
That's right. So keep an eye on the press releases tomorrow that we're putting out. It goes live at 10 a.m. After that, you'll see an event on Google Plus where where I have scheduled a hangout for the next Thursday. Dr. Carol Christian and I will be talking with the principal investigator, and we will talk all about that press release. And that's all I'll say for now. That's next Thursday. So I guess that's it for this week, Space fans. I'm sorry. I guess that's
Hubble
it for
fans.
I will thank you all for watching, and as always, keep looking up.
Ideas and then be able to explain them to the public. I mean, because you're taking something that's at the cutting edge of science. What we do in our press releases, we're really at the edge of science, and we've got to provide all the context and all of the background information to bring it out to the public. And so this is what really, jazzes me about doing all of this stuff with Tony and with all the stuff we do in the Office of Public Outreach, is that understanding not just the discovery, but all the context and the background behind it. So, Tony, did I vamp enough to cover up?
You did great, thank you.
Thank
I found
you.
the tab that had the YouTube video in it and killed it. I have like 300 tabs up on my desktop right now, and every time I think I've get it, there's always one that gets through me. So, again, apologies for doing that yet again, but you know what? I don't think people would feel right if I didn't do that at least once during the Hangout. So
look, it's live, okay?
It's live, that's right. So anyway.
And it's free, so you're getting what you pay for.
That's That's right. So here we are. Another month has gone by. We have started, by the way, broadcasting the public lecture series that Frank hosts every month at the Institute. The first Tuesday of every month is now going on our YouTube channel. So we hope that you guys will tune in to watch that as well with us, because it's an easier way for you to interact. What we try to do is answer any questions and comments while it's going on. I'll monitor the Twitterverse and the comments on YouTube and try to respond to them while the lecture's going on. And Frank will do that to the extent that he can, but he's also got to run the bunch of diffraction spikes from the telescope, and then there's the saturation in the center. That's the star, right?
Right. Exactly. And the thing about Hubble is that over the years we've learned the characteristics of Hubble incredibly carefully. And one of the most important characteristics is called the point spread function. So here's some cool stuff that I can give you that I can't do to the normal public audience. And so the point spread function takes, stars are points of light. And it's a very faint point of light. It appears as a circular dot, and as it gets brighter and brighter, it becomes bigger and bigger dot, and then it starts to develop these diffraction spikes and all of this stuff around it. And so with Hubble, we've gotten very good at characterizing how that point spread function grows and what is the shape of the light that is put onto the detector. Using that information, we can very, very carefully subtract out the point spread function due to the Hubble detector, pull out that star, and in the right-hand image, you again see 3 dots of light. And those are the planets, yes.
Oh, okay, those are the planets, yeah.
Right. Those are the same planets that Keck had discovered a few years earlier. But the important point was this image was taken, I think it was 8 years before the Keck discovery. So it adds to the baseline of this discovery of the planet. So we have more points in the orbit for these planets around its parent star. And that's really important. When we discovered Uranus, the first thing people did was go back into old data to see if you could, like glop in the middle, is the residue after subtracting out the light of the star, right? If you're trying to look for things around a star, you've got this honking bright star that you've got to be able to subtract out. So the folks at the Keck Observatory subtracted out the light of the star, and that psychedelic residue in the middle is the result of that subtraction. So you got the star mostly subtracted out, but the red dots around it are 3 planets that were discovered.
July?
Yeah, the ones that the red dots, and then there are the pluses to show where the planets were observed in July 2004, and the dots show where they were in 2008.
Got it.
Okay, and showing that they're moving around this star. right? And so this was one of the first discoveries of actually observing planets around another star. And this was actually done with the Keck telescope from the ground in the infrared. Now, we here at Hubble didn't do this. This was again from Keck. But what we did with Hubble is we came back a couple years later, and we looked not at a new image of HR 8799, but we looked at an old image that was in the Hubble database. All right, the Hubble archive's got lots of cool data in it, and so people went back to it, and you see on the left the incredible brightness of the star HR 8799 as it was observed in the Hubble database, the Hubble archive. Well, subtracting...
So you can see a bunch of... So what you're looking at is a... Hello, everybody. Welcome to our latest Hubble Hangout. My name is Tony Darnell. I am at the Space Telescope Science Institute, and it is that time of the month where...
Oh, great phrasing, Tony. I love it.
So it is time now for our monthly visit with Dr. Frank Summers, the outreach astronomer at the Space Telescope Science Institute, who keeps tabs on all of the really cool and interesting things going on with Hubble and shares them with us every... Welcome to our latest Hubble Hangout. I did it again. Tony Darnell. I am at the Space Telescope Science Institute, and it is that time of the... If I wish I had $1 for every time I've done this.
Okay. You're the expert here, Tony. So
now I've got to figure out where it is. Gosh, darn it.
Your echo is coming out somewhere.
Oh, I did it again.
And you get to hear your mistake coming at you twice. So while Tony figures that out, I'll just say that it's always fun for me to be here, even if I am considered that time of the month for Tony. But what we like to do here at the Space Telescope is we really get a lot of fun out of taking the deepest discoveries from Hubble and explaining them in detail. Because for me as an astrophysicist, the really difficult thing is to have a wide breadth of all these various
shows. So it's a little bit, he may or may not be able to respond to all comments. Okay, Frank. So what do we got? We got
okay.
What's the latest and greatest with Hubble this month?
All right. So I know I did it live last week during the public lecture series, but I know a good amount of this audience probably hadn't seen it. But I want to go quickly through the news from the universe that I did last week, and then I want to go beyond what I did with the news from the universe and talk about a new section on Hubble site that I had a lot to do with, and I think is really, really cool. Okay.
Agreed. Okay. Let's go.
So let me. I got to start my screen share. There we go. Starting my screen share, and I'll start the PowerPoint slides. Okay, so when I present this to the public lecture series, I call it News from the Universe, and this is the stuff. This is the stories I chose for May 2014. So my first story I called 5 Golden Rings. For those of you who know the Christmas song, well, it doesn't have anything to do with the Christmas song. So what we're talking about is looking at and discovering new information in old data. Now, I bring up this image. This is from the Keck telescope, not from the Hubble. This is of the star HR 8799. Well, actually, it's of everything but the star HR 8799, because
so is that like a star from the 60s or something? It looks like, like
yes,
a cyanide star. What's up with those colors?
This star went psychedelic on us. No, all that psychedelic